Hi everyone, I am Akash and I am currently an ML engineer at a tech startup. So let's get directly to the point that we all know that ChatGPT is something which everyone uses, and it turns out that it is really helpful for our day-to-day activities, irrespective of the domain in which we are using it, right? Whether it be coding or reasoning, although reasoning is currently a domain which is been explored. Yeah, I mean, there are people or professors who are exploring this ability of reasoning from complex reasonings through this GPTs and like Claude GPTs and other models, right? So my point being, these are the models which are like really helpful, and like I have I haven't trained a model as such from my end, but I wanted to explore about how these models are currently being trained, right? And I mean, yeah, so this is a paper, like came out on 7th March 2024 by the team from 01.ai, right? And the model name is YI, Open Foundation Models by 01.ai. So like it gives in a depth about what these models are, how they have been trained, how the data has been curated, how the architectural changes has been selected as such, and like then how the context window has been scaled, how the vision backbone has been included so that it makes be a multimodal model, right? And I mean, yeah, it's quite cool. And by the way, it's also multilingual, right? So multilingual in the sense currently it's supporting two languages, but the same patterns can be expanded to other languages as such, right? So I mean, this is quite a good paper, and if you summarize it, it's basically solving a machine learning problem, with the first principle approaches, right? And I mean, yeah, so I really like this paper a lot. And when you see this LMSys chatbot arena, which actually determines how a model, the scores for the model, you see that the YI model is just behind Claude and GPT and Gemini, right? So that means that something is quite good, or the direction in which this model has been trained is quite good, right? So we can trust it, and then from there we can learn about how these models are being trained. And probably we can also know about, there can be a lot of learnings about how the data has been curated, and if the data is the nature of the data reflects the behavior of the model, right? So we can be more sure about where the model could fail, what are the applications and use cases it can be used for. And I mean, yeah, so like there are a lot of things that has been like quite cool about this. I have written a summary of it myself. I would wish I can share it as well, but I mean, yeah, it's quite cool, right? So let's first of all, before going into the paper as such, let's make a mental map about how this model would like how these foundation models are being trained. So step one, right? This model, high chances are that the model would be a decoder model. What decoder model does is it takes in an input and then it produces the tokens based on those input, right? So let's not talk about RLHF and so on. So the basic step would be an auto-regressive nature, right? So it would just complete those tokens. The Let's say that the cat is climbing the wall. Now, let's say that there is a auto-regressive. What auto-regressiveness means is based on token by token prediction, right? Like just continue regressing yourself. I think I hope I'm right. So yeah, so you continue predicting the next set of tokens, right? So this is what simply a decoder, like this is what a function of decoder is like, right? And probably it can be an encoder decoder as well, but most like what I have seen is that you take a decoder model. These are my reasonings because on based on what I have understood, right? So I mean, yeah, you can reason my reasonings, and then probably you can come out that okay, this is something which needs some rectification, and let me know, right? So I mean, yeah, the first step would be that let's choose the model that this before training this model, our objective is that we need to just train a model which predicts the next set of tokens. Next step would be to, so the architectural behavior would be around decoder model. And what a decoder model, basically transformer model, right? I mean, the model which would be used for this decoding task is a transform model. And what is a transform model? It's basically like, basically the high level overview is that it's due to the nature of its attention, this model turns out to be quite useful when we scale it up, right? So um, a simple intuition can be, let's say that my name is Akarsh, and now I ask a question: who is the guy? What is the name of the boy? Right. So now you focus on the questions. Like as a human, what we do is we focus on the questions context about what is the context about asking the name, right? And in the entire sentence, the focus is around the Akarsh word, right? So you attended this name and the Akarsh word, right? So this attention is quite something intuitive like this. I can say that, although I'm not getting into the mathematical detail, but this is what, if I can explain it in layman's terms, it is something like this, right? So I mean, the transform model is there, a decoder model. I mean, yeah, decoder. We would be choosing a decoder and a transform model for it, right? The next step would be getting a good quality of data. Third would be about training it. So training relates to much of the infrastructural changes, like making sure that the gradients are like clipped, the weights have been properly initialized so that the gradients doesn't get exploded, setting appropriate learning rate, and currently like for cosine decay has been used, right? So I mean, the intuition being that if I'm solving this machine learning problem of making a foundation model, I would be going into the history literature about how these models are being currently trained, what are the trade-offs, what are the best practices, have anybody else approached this problem in the past, right? And from there on, I can take some learnings and then try to make come up with a solution, right? So yeah, so step one, taking a decoder model. What kind of decoder model? Basically a transformer. So why transformer models? Because of the attention mechanism. And there is one more thing, that before transformers, LSTMs and RNNs used to come, but the problem with that is that the training or the inference training isn't parallelizable. Parallelizable in the sense, what LSTM or RNN does is that you have, let's say, what before going into that, uh, I mean, I'm going a bit fast. Take it slow. Yeah, there might be confusions out here, but it's okay. Like you can explore it, or you can ask. I mean, yeah. So what happens is that there is a term called token, right? So what token basically does is, it actually comes from the fact that we want to so computers cannot understand in text, and basically it needs to understand in numbers, right? So what happens is that we create some amount create a function which maps this sentences into numbers, right? So but so now this function mapping is actually trained, right? So it assigns, let's say Akash is a word, right? And probably from the training it assigns that, okay, AK can be one mapped to a number, and ARSH can be mapped to another number, right? So I'm not going into the technical details because I'm more concerned about this paper, but I'm just trying to give a high level overview of how these things work. So basically, it comes from the data compression technique. I think byte pair encoding is something which is being used. Yeah. So essentially, what we do is that we map. So yeah, I mean, yeah, where we were at that stage where the model are not parallelizable, right? So what used to happen is that whenever sentence is given as an input, we tokenize it, right? And what we tokenize into something known as tokens. What are these tokens? Just an encoding, right? So what used to happen was that while training it, an LSTM or a RNN, what it used to does is that it used to take one token at a time, predict a hidden state, and then pass it to the another token, and so on. So right, you see that this the solution. I mean the you're just sequentially passing it, right? So it's not parallelizable as such. So so from there on, this transformers came, and what it does is that it parallelized this. How did it parallelize? I mean, yeah, you just attend to the tokens which are necessary for you for generating the context. uh, yeah, so I forgot where so this is all about the transformers and basic understanding of what this tokens and so on are, right? So yeah, coming to the paper as such, step one, we know that now the model which we need is a decoder model. In specifically, decoder means transformer model. I'm not writing it down right here, but I mean we can just think of it probably. And then the second step is getting the good amount of data, and the third step is infrastructure, right? Making sure that for this training and so on, you have good infrastructure setup, you have a good training mechanism, and checkpoint savings, list stoppings, model callbacks, and so on, right? So yeah, let's get started with this. So in this paper, the author says that we introduce a YI model, the YI model family, a series of language and multimodal models that demonstrate strong multidimensional capabilities. What are these multidimensional capabilities? In case of, you can see it in terms of going through complex reasoning tasks, or generating articles, domain specific tasks, or probably vision language tasks, right? So I mean, yeah, this is how multi dimensions currently be. The YA model family is based on 6 billion and 34 billion pre-trained language models. Again, what are the 6 billion and 34 billion? These are just the parameters of a model, right? So, yeah, I mean, yeah, parameters of this model. Then we extend them to chat models, 200K long context models, depth upscale models, and vision language models. What are these chat models? Basically, Chat GPT, right? So, what you want a model to be helpful. So, what you do is that you make it like, I hope the audience here is familiar with the deep learning, basic deep learning. So there is a thing called fine tuning, right? So what we do is that we have a pre-trained model, and we fine tune it to some of our specific tasks. So this is exactly what it means. That chat models means we extend them to chat models. We are just training it to be act like a chat. 200K long context models. So what this 200K long context means, that now this tokens, right, when we split it, or we map this sentence into tokens, um, you get this length of a token, right? And now what they say is that we extend this capability 200K long context window, right? So I mean, it's quite big as such. I mean, you can understand that one token can roughly be around 3 to 4 characters, right? So, or it is said that it is said that one token is 0.75 words. So yeah, that is the exact max. Yeah. So depth upscale model and vision language models, right? So the story being that firstly this model is trained on some language tasks, and then once this model gets pre-trained on the language tasks, right? And then now a variety of domain specific applications happen here. So our base models achieve strong performance on a wide range of benchmarks like MMLU, and fine-tuned chat models deliver strong human preference rate. Building upon our own scalable supercomputing infrastructure and classical transformer architecture, we attribute the performance of YI model primarily to its data quality, right? So a model is as good as the data that it consumes. Like similarly, as a humans, whatever we consume, the same thoughts comes into our mind, right? So this is the exact in any deep learning based problem. Although architecture is not a subsidiary, but it's all important part. But more important lies in the attribute, the data attribute, that how good the data is, how well the problem has been framed, then how diverse the data is, right? So yeah, that is the exact thing, that this entire paper is more about that, knowing that the quality of data is important, and yeah, taking the best practices from the modeling of the literature, and making sure that the infrastructure is good. Yeah, that's it. For pre-training, we construct 3.1 trillion tokens of English and Chinese corpora using a cascaded data deduplication and quality filtering pipeline. For fine-tuning, we polish a small-scale instruction dataset. For vision language, we combine the chat language model with a vision transformer, and we further extend the context window to 200K, right? So we believe that our current results, continuing to scale up model parameters using thoroughly optimized data, will lead to even stronger frontier models, right? So I mean, I have been repeating the same story, but yeah, it's good to repeat things, so that at least you take only the things which are like summaries, but yeah, you can dig down deep into it. So first step is that making sure that the data is good. Second is infrastructure, I mean modeling, and third is infrastructure. And how would we be using these models? Firstly, we would be pre-training it, and then we would be using it for our domain-specific applications. Now, why does this pre-training help, right? So it's like, I think the initial set of results came from ResNet model, probably around that time, where in CV um, in CV it proved that the pre-training helps a lot. So from there on, then I think BERT came in. BERT like popularized this set of pre-training for mask language modeling and next sentence prediction. And from there on, this pre-training helped, right? Like I mean, the pre-training proved that it's helpful to do pre-training and then followed by fine-tuning on some domain specific application. So what actually exactly does pre-training does in the case of like this YI model, right? So what we do is that we ask the model to predict the next sentence or next token based on all the previous tokens. That's it, nothing else. So what can be the case? Like the cat jumped on a wall. The next sentence can be the cat jumped the wall. I mean, the following the jump of the wall, the cat drank the milk, or probably it landed on the roof or so, right? So you're just saying you're just giving the model a rough context around the knowledge of the world, right? So that is what exactly is pre-training. And then what fine tuning does is that you have some domain specific data, like as a let's assume that as a kid when we grow, we are like seeing this world, right? And then following let's say I'm in 10th class, so I'm knowing more about trigonometry and so on. So probably that can be a good example that now, although I have a good knowledge about the world, how it works and so on, a bit about maths and a bit about behavioral and so on, but now if I want to just learn more about trigonometry, I would be fine tuning my um, probably my brain to know more about this, right? Yeah, so that's like just an analogy. So what basically in pre-training help is that you make the good data, you select the appropriate tokenization, the appropriate model architecture. That's it. And the first principle based approach is that you just get a good quality of data, and now I mean a lot of things are there. Then the step is fine tuning followed by infrastructure changes. And yeah, I mean I forgot one more thing, that although you have trained, it's good to the fourth step is going having a goal test data set, which have all the diversity that you would be probably facing in the production, right? So that is the fourth step. I missed it. Yeah. So in context learning, base model performance, main results, in context learning, chat model performance. Although the paper is a bit long, right? I think I would be continuing from here. So yeah, right. So these are my learnings from those paper as such, right? So yeah, let's let's get first to the pre-training data. So in our pre-training data, what it does is what they say is that our approach to pre-training is to train a standard dense transformer architecture on a heavily engineered large pre-training corpora, where our underlying assumption is that when trained on extensive data of high quality, a standard architecture can exhibit advanced capabilities, right? So no, not much changes in the modeling, but more engineering, heavy engineering on the data side, and that definitely makes sense. Knowing the data is exactly the thing, right? So I'm not preaching, but I mean, yeah, this is my learning. This is to say that we may not need much architectural modifications. So how do they do this pre-training? I mean, what is this data cleaning pipeline here? So they collect the data from the raw web data. Firstly, they filter the language of it, right? Because I mean, I think they have mentioned that in the they have been training it for Chinese and English language, right? So definitely that makes sense to just train a simple classifier which would just predict the language of the input text. Then there is a text metric filtering, repetitive document removal. So what repetition basically says is that um, make your data unique. So what happens is that probably repetitions comes into play, right? If you just give duplicate data, what happens is that the model is repeatedly saying the those specific parts, and probably if some context similar to that arrives, which is of repetition, probably the model would just repeat itself, right? And it won't have much creativity at that part. Rule based corrections, perplexity filtering, document quality filtering, paragraph deduplication. So deduplication is a quite a good thing here. I mean hash exact deduplication, and semantic filtering, topic filtering, and safety filtering. I mean I hope I have written it. Huh, no worries. So yep, I think I think that's an important part. So let's do it here. Just a second. Hmm. So the filters are here. Heuristic based filtering, this part of the filter aims for removing text of low quality, right? So URLs, a domain, block list, and garbled text filters, document length. The filtering thresholds are based on statistical analysis of large document samples. Although I haven't seen their code base of pre-training, but I mean it's good to know that they have something where we can, I mean, those are some filters which can improve the quality of data. And there are some learned filters. We use learned filters to address nuanced cases that exceed the capabilities of standard heuristic rules. Notably, the Chinese content extracted particularly with a high ratio of inappropriate content present. So what they do is that there is a perplexity scorer evaluates a vast array of web documents and discard those with perplexity score largely over an average, right? So what let's see that what perplexity score is, right? It is a direct measure of a model's linguistic competence, with lower score indicating superior language processing capabilities, and it is a measure in NLP, right, to evaluate the performance of language models. So that makes sense, right? You are just evaluating your models based on some scoring. And the second is the quality scorer is classified trained to recognize and favor pages that have qualities similar to Wikipedia, right? Because Wikipedia has it in itself a good what do you say? You see that a Wikipedia's page is structured in a like introduction, then the main content, and the endings with the reference, right? So that says that the quality of the document or article in Wikipedia is quite good. So they're trying to follow the same approach. Document coherence scorer identifies low quality web documents that consist of disparate sentences or paragraphs, and safety scorer identifies and removes web documents containing toxic contents, right? Yeah, then there is cluster based filtering. We further use unsupervised semantic clustering to group web documents. This clustering feature process enables efficient identification and analysis of document sharing similar semantic feature, right? So yeah, that definitely makes sense. That let's say that you have a large millions of documents. Now, when you are able to cluster and say that okay, this cluster has a specific topic, and let's say that I want to take some data. Let's say my model is not performing well on articles, right? So what I can do is that from those clusters I can identify the patterns or increase those, take more data from those cluster to let my model improve its ability on the articles, right? So or in a more important or yeah, so in a more intuitive way we can say that at least we know that this is the data distribution of articles, this is the data distribution of probably mathematics for reasoning and so on. And now I can exactly argue that if my model is not able to perform more well on mathematics, probably this cluster has something or some patterns which my model is not able to capture. Let me add those more data points more into my model training, right? So that is, I think, a good way. Document identified as low quality through automated and manual verification excluded. Deduplication is quite a good thing. I think there was a instant United Transformers from the course from Stanford. There like they did mention about this paper, and I think they I would be citing a sentence, roughly a sentence, that what they there was an experiment where they tried training the data on the repetitive documents, and when removing those repetitive documents they found that model improves its performance on some benchmarks, right? So yeah, I mean, definitely removing those duplicates helped a lot. Yeah, coming to the tokenization, we use byte pair encoding implemented in sentence pins framework. So yeah, so what basically tokenization does is that the inspiration of this byte pair encoding actually comes from data compression technique. So what data compression does is that you assign a set of characters into a specific encoding. That's it, right? So let's say that in my vocabulary A, B, C, D, and up to Z, right, are mapped from 1 to 26, right? And now let's say that there is a frequent repetitive character of AA or triple A or AAB, right? So why don't I just assign this subword a number, right? So this frequency actually this taking knowing this frequency of this subword actually comes from the data on which you have trained this tokenization. So yeah, so in our case currently the vocabulary size was 1 to 26 if I just map from A to Z. right? But the problem with this is, let's say that there is a word called Akarsh. So you would be just mapping one, then whatever the case mapping is, then again one because A. So now you see that there are six tokens being generated. What if now the problem is that this token, the complexity, algorithmic complexity of this attention mechanism is actually coming out to be O of n square. So as your sequence length or this token length increases, your computation would increase, right? So here is exactly where the data compression technique and this tokenization comes into play. I mean, we are already doing tokenization by just doing one, two, three, like I mean, a occurs each character mapping to some number. But now, I mean, this byte pair encoding technique, we just pair and assign a number, right? So let's say that AK is something which is repeatedly coming. So now, on based on the frequency, we'll be assigning a number to it. So yeah, that's it. And we allow RAID characters to fall back to Unicode byte encoding. We employ an identity tokenizer to avoid transferring all punctuations to half width format. And yeah, I mean, there are some nitty gritties which they have definitely taken into account. We do not use this approach because as a LLMs prioritizing English usually utilize dummy prefix, right, at the beginning. Yeah, so to generalize the same word at different positions, and we do not use this approach. So yeah, that is the tokenization. So tokenization is basically a standard process. There are not much innovations out there. Just that I think they have already mentioned that there are some numbers. We split numbers into individual digits, so that one is assigned to some token, two is assigned to it. Not like, let's say that in Akkars we can say that, right, AK is assigned to something. Let's say in our vocabulary, 12 is something which gets assigned repeated, frequently repeated, right? So we won't be assigning a token to it. That's it. The models are hidden size 4096, query head KV head 4, layers are 32, retrain sequence like this 4096, and max learning rate is 3 e power minus 4. Right. So what this hidden size actually is, hidden size is basically, I think, I hope, yeah. So hidden size, let me check it. I think we would be using it. Yeah, I mean, hidden size is something that, let's say you have got these tokens, right? So what do you do now is that you map these tokens to some vector space. Let's say that this token has represents some. So what this vector space actually is, that this, you can, in intuitive way, you can understand it by just saying that, okay, my word represents 0.96 times the adjective. Let's say that there are like 4096 features out there, one being adjective, one being the pronoun, like the grammatical and semantics of that token, right? So I mean, yeah, that is where the 14096 comes into play. uh, Q heads and KV heads, I think this is more of the attention mechanism. Yeah, and 32 hidden layers are present. Pre-training sequence length, right? So sequence length, we mentioned this in Akash. Let's say that if we are tokenizing at each character, the sequence length becomes 6, right? So yeah, that is how the 4096 sequence length comes into play. um, and now the tokenization has been compared, the data has been taken into, like, considered, and the attention mechanism is here, right? That Llama 2 use group query attention only on its largest model. In it 7B and 13B uses full attention. We incorporate group query attention in both YI6B and YI34B. Mm-hmm. I hope I have written it. It's not much complex as such. Um, I mean, yeah, we can Google, we can Google it as well. So, and the activation function is Swiglu, right? Reducing its activation size from 4H to 8 by 3H, and positional embedding and long context. So, for the positional embedding, I think, the proven method is using rotary position embedding. So, following the standard implementation. So, what basically rotary position embedding does is that in the paper itself, they mentioned that, there is a need for capturing the absolute position encoding as well as the relative position encoding of a word with respect to all the other words, right? So yeah, I mean, it brings in the mechanism for the same. Yeah, I also made a video for it because To adapt the base model to longer context, we continue pre-training the model on 10 billion more tokens from our pre-training data mixture. um, let's see one of the data composition. So you see that the most of the data is from the web page, then there is code, paper, some comes from books. So if you want some creative, high chances that the creativity comes from the books, right? There's encyclopedia and others. So now you can see that okay, this model would be having some ability from of coding, some papers, books and other things, right? So we can just make it out from the data. And I hope what's the our fine tuning method significantly emphasizes data quality over quantity. And there is one more good thing about the model that yeah so what they mention is that while doing the fine tuning, so once you have pre-trained the model, so the model now at least knows the knowledge about the world, that now what should I predict next based on my context window, right? A context. Now for the fine tuning, our purpose is to make this model more oriented towards helping as a chat assistant, right? So what we would be doing is basically providing the data related to the chats, like how a assistant behaves. And one more thing that they use is that I think that now for preparing this data, they need to make sure that the quality is good and that there is good quantity of it, right? So what you basically do is that what they did was that they have their ML engineers there. So each of those samples used to pass through all of those ML engineers to because they exactly know, right, that how a data should be like. And from there on they prepare the data to reduce we spend extra efforts on reducing hallucination and repetition. Yeah. So and there are basically some formats out which they have been taking to yeah, like there is a format, right, that you input a system message and then a user message, and for the few short examples you provide an assistant user and so on. So that is the exact format that they have used. We use the next word prediction loss for fine tuning. So yeah, so what you do is that there is a sequence, you just shift the entire sequence to the right, and that becomes your label, right? And then you just train the model. We use Adam optimizer, and epsilon is set to this with the noise. And yeah, I mean there was one more good thing, that in the infrastructure side, they have their monitoring, they monitor the computing resources, improve the training speed from optimized parallel strategies, kernel efficiency and long context support, right? And unified fine tuning framework support, distributed training backend, like you have multi GPU. So I think there is one more thing, that the gradient spike, right? So and multi GPU trainings, I'm not sure, I think it's half knowledge, but anyways. So yeah, I think in the paper as well they mentioned that they have handled it quite well. And yeah, for fast and efficient inferencing, you use quantization, dynamic batching, page at attention, right? For and yeah, KV caching is something which is I think used a lot. They evaluate across common sense reasoning, reading comprehension, maths, code, etc. Yeah. So one more thing is that for the safety as such, I think to enhance the model's trustworthiness and safety, we develop a full stack responsible AI safety engine, right? It ensures safe pre-training, alignment, and deployment. So what they do is that in the so there are two stages where the model has seen the data, in pre-training and fine-tuning. Why not just make sure that those let's define first of all what the safety means, and then include it in our training and the pre-training and the fine-tuning data set, right? So yeah, I mean that's more or less about it. Common sense reasoning. So these are the evaluations. Turns out that they have really performed well here, right? So the entire thing is more around making sure the data is good, taking inspirations from the best practices of the model, infrastructure management, and yeah. Although this sounds easy, this definitely isn't easy, but yeah, I mean that's it. I think yeah. There are more details, but I mean yeah, this was what I was planning for this video. Basic high level overview of this model. And let me think. I think there are a few more things which I say. Yeah. So in designing YI model series, we are mostly concerned with the following dimensions, right? When choosing model scale, the desire is to have a small enough model, right, for inferencing, faster inferencing, but also good enough model to generate the reasoning. So that's why we use 34 billion model. And emergent abilities. So in addition to the steady quantitative improvements, the scaling process also leads to interesting qualitative behavior. As LLMs are scaled, they hit a series of critical scales at which new abilities are unlocked. They are not directly trained on those tasks, but they understand it quite well, right? Yeah. By the way, there was one more thing, that although we have created the data and trained a model, how much quality of data is good enough, right? How What should be the scale of training, right? How much epoch should we be training on? What are the sizes of the models that we should be training on? So yeah, that was something I didn't complete. I mean, I missed it. But yeah, so what they do is that they took the learnings from Chinchilla scaling law, which which basically says that okay, you need to scale the data and the model in the same proportions, right? And what they then finally did was that they increased the pre-training data 3.1 trillion tokens to compensate for a decreased compute flops, because they were training a 34 billion instead of a 70 billion model. This make the model data scale combination fall into the post chinchilla optimal region. So there is a optimal region, and I think I mentioned it here. They are training a 34 billion model, and they should be training for 1.56 trillion tokens, but now they are training it for 3.1 trillion tokens, right? So they are making it sure that it falls in the post um, chinchilla model region. So yeah, I think this was it. Yeah. So yeah, that's it. These were my understandings. This is not. I won't be saying that this is actually true. Like whatever I said is true. But I mean, yeah. Just I wanted to share the learnings, and probably there are things where I can improve. And yeah, that's it from my side. Thanks.